audible?
Yes.
Okay.
You are audible, but your voice is bit. Yes, you are audible.
Okay, is it better now?
Now it is better.
Okay, fine. Should I start or are we waiting?
Yes, we cannot see your video. So welcome.
Yes, thank you.
So participants, it is my pleasure to introduce you to Dr. Pyari Mohan Pradhan. He has done his MTech degree from National Institute of Technology, Raulkela, and PhD degree from School of Electrical Sciences, Indian Institute of Technology, Bhubaneswar. And presently he is working as Associate Professor at Department of Electronics and Communication Engineering, Indian Institute of Technology, Roorkee. And Professor P.M. Pradhan has very vast experience in India and abroad, and he has written multiple popular articles, and today he will be delivering about the application of the optimization algorithm for cognitive radio and wireless sensor network application. So over to you, Dr. Pradhan.
Okay, thank you very much, Dr. Nanda. Those were very kind words introducing myself. So good evening to all the attendees as well as all the panelists. So let me share these slides and then we can start. So is the title slide visible?
Yes, title slide is visible and perfect.
And it's working, right? Outline is now
Yes,
visible.
it is working fine. Yeah.
Okay, fine. Thank you. Okay. As informed by Dr. Nanda, I would be uh, giving a talk on multi-objective optimization and its algorithms. You know, I'll not be touching upon the multi-objective algorithms, but I'll be mostly focusing on the application side. And I have picked up two different applications. One is in the field of cognitive radio, and the other one is in the field of wireless sensor network. So I'll be giving brief idea regarding cognitive radio and wireless sensor network before getting into the multi-objective problems and how those have been solved using multi-objective algorithms. So the brief outline of my talk would be I'll be just introducing what exactly is a cognitive radio network, how this is linked to the spectrum sensing or cooperative spectrum sensing, and what are the multi-objective problems in cooperative spectrum sensing, and how they are solved using multi-objective optimization algorithms. The second application is again in the field of cognitive radio only, and that is focused on cognitive radio engine. So we'll see how the multi-objective optimization algorithms can be used in the field of cognitive radio engine. The third application is in the field of wireless sensor network, where we will see how the layout or how the sensor nodes are deployed in an area using multi-objective optimization algorithms. So those are the three applications that I would be touching upon in this talk. So before getting into the multi-objective problems, let's look at the cognitive radio briefly. So when we look at the spectrum occupancy is shown in this slide. On the left side, you can see various kinds of applications, and the bar chart shows how much spectrum is occupied by these applications. So effectively, if you look at the maximum spectrum occupancy, that comes around 26%, 27%, that too in a specific TV band. So, when we look at the cell phone or unlicensed band, those are also, having some kind of spectrum occupancy, but it's not up to the 100% as we feel while we are talking over phone, we feel that the spectrum is completely occupied and we are getting busy tones. So, looking at all these applications, we can have a feel that the spectrum can be utilized more efficiently. And to do that, we need some of the help from multi-objective optimization algorithms. How they are used in these applications, we will have a look at it down the line. So the major motivation behind getting into cognitive radio is we do have a lack of interoperability between different technologies. Say, for example, we looked at different technologies in this particular slide, where there are technologies which are defined for TV, technologies which are defined for cell phone, technologies which are defined for satellite applications. So various kinds of technologies are there, but there is very lack of interoperability between different technologies. And the second point is there is a lack of spectrum. Whether there is really a lack of spectrum or the spectrum is being underutilized, that is what the cognitive radio focuses on. And so if you look at the spectrum related facts, the spectrum, if you look at the way the spectrum is auctioned in India or in other countries also, those are fixed spectrum assignments. So every company, whether it's Geo or BSNL or any company, they have a fixed spectrum being assigned to them. So, and the amount of money they spend in acquiring these spectrum is huge. So the bandwidth is very, very expensive, and the usable frequencies are already taken by by different applications. But if you look at the recent measurements by the FCC, it will show that the spectra that have been allocated to different technologies, not only the cellular application, but all other technologies, you will see that the measurements are actually not fully utilized. Okay. So, and on top of that, you can see time scale of the spectrum occupancy. The time scale will vary from milliseconds to hours. So sometimes a particular satellite band is occupied for hours. Let's say, if you look at the night time, the people would like to view this, view TV, and similarly, if you look at the cellular communication, there are few time slots in a day where the spectrum would be fully occupied, right? But there are other slots also where the spectrum is very, very rarely occupied. Okay. So that is what the spectrum facts are all about. So the solutions to these problems are to design a radio which is more clever in nature and which is more frequency agile, so that it should be able to recognize which frequency is free at what time, so that that particular frequency can be used uh, by different technologies. Not only the particular assigned technology, but any other technology can use that frequency at that time slot based on the interoperability between different technologies. So the third one is the spectrum share between different technologies or different companies. Now, it is very rare to find that kind of sharing between companies, but of course, the technologies can share the spectra if the spectra is not fully utilized. So, in the context of cognitive radio, the term spectrum whole is a big focus, where we look at the axis in terms of time and frequency and power. So, if you look at the figure, we have x-axis as time, y-axis as frequency. So that means in the time frequency plane, I have individual grids, and each of these grids are representing a slot that has been given to a particular technology. So that means if a particular slot is not being used, then that particular slot is called a spectrum hole. So you can see that The spectrum holes are those spots where there is there are no boxes being drawn. So those are your spectrum holes, and the boxes are showing where the spectrum is being used by different technologies. Now the power, we can see the power is zero or very negligible when it comes to a spectrum hole. Okay. And what we want is we want to use these spectrum holes, but the spectrum holes are not continuous in time, as well as they are also not continuous in frequency. And you can see those have been shown using arrow marks, that the spectrum hole is continuously changing over time as well as in frequency. So that is the reason that if you want to access these spectrum holes, it needs to be very, very dynamic in nature. So you need a dynamic spectrum access technology to exploit these spectrum holes. So to find out the spectrum hole, so the basic idea is to let's say you record the samples for certain duration, and then if you feel that the energy of the signal that has been received is less than the threshold, that means there have been no regular signal transmission in that particular time and frequency slot. So that is how the easiest energy detector based spectrum hole detection works. Now, where this multi-objective optimization algorithms come into picture? Okay, so let's look at some basics of cooperative spectrum sensing. So this figure shows the cooperative spectrum sensing framework. Uh, on the left side, the CR stands for cognitive radios. So we have CR1, CR2, CRM. So there are M cognitive radio users, and you can see that the next block shows summation of mod square, that is nothing but calculation of energy by each of the cognitive radio users. So the cognitive radio user receives something. Let's say the radio user 1 receives Y1K, and it calculates energy over samples, let's say 100 samples or 1000 samples. Okay, and that energy that has been calculated has been denoted by U1, U2, UM. Let's say the noise component that has been included in the received signal is modeled as V1, V2, and VM. So what this cooperative spectrum sensing framework says, that instead of a single user detecting the spectrum hole, is it possible for multiple users to collaborate? Okay, so that is where the cooperative term comes up. Is it possible for multiple users to collaborate and then decide whether the time frequency slot is a spectrum hole or not? So a single user can do that, but there are problems. Say, for example, imagine a scenario that there are two users on either side of a mountain, and the second user is the second user is feeling that the time frequency slot is empty because it is not receiving any energy uh, in terms of the received signal, but practically that signal is not received by the second user because he is on the other side of the mountain. Okay, so that is called as hidden terminal problem. The terminals are hidden, means the users are hidden from each other, so one doesn't recognize the other, or vice versa. So in those scenarios, what we can do is we can go for cooperative spectrum sensing. So instead of two users detecting the spectrum hole themselves, is it possible for them to collaborate and decide that the time frequency slot is a spectrum hole or not? Okay. So that is where the fusion center shows up. So the fusion center's job is to get the get the decisions from individual cognitive radio users, and then decide based on the fusion of these values whether the time frequency point grid point or the time frequency slot is a spectrum hole or not. So that is based on certain threshold, and that is carried out by the decision device. Okay. So now if you look at this particular framework, there are some weights shown in the figure, W1, W2, Wm. The weights are shown to indicate how much weightage should be given to the decision taken by individual cognitive radio user. So, for example, if say for example, your cognitive radio user 2 is close to fusion center, you expect that whatever has been transmitted by the cognitive radio user 2 would be more accurately received by fusion center than other users who are far away from the fusion center. Okay, so in that case, W2 would be a high value, whereas other values of W1, W3, all those values would be less because they are far away from the fusion center. So the transmission and reception accuracy that we have at the fusion center would get affected because of that distance. Okay. So the parameters which need to be fine-tuned here is the weight vector, which consists of W1, W2, Wm. Okay. And whether when you look at your fusion center, you decide whether the slot is a spectrum hole or not by comparing the total energy with certain threshold, right? So that threshold is again another parameter which needs to be taken care of. Okay, so effectively we have W1, W2, all those weight values along with the threshold value which needs to be taken care of. So that's where the multi-objective optimization shows up. Now, I guess the different algorithms for multi-objective optimization have been taught to you. So the two objectives that I am going to touch upon in this application is probability of false alarm and probability of detection. Now, false alarm is, for example, if you go back to the spectrum hole, let's say there was no spectrum hole, but because of error in the decision, you assumed that there is a spectrum hole and you started transmitting in that particular time frequency slot, whereas some user was already transmitting in that. Okay, that is one case. The other case is there is a spectrum hole, but you couldn't recognize it. You falsely recognized it as a slot which has already been used by the users. So in that case, the spectrum hole remains vacant, but you are not using it. So those two cases have been taken up as false alarm and detection. Detection is if you are correctly detecting the spectrum hole. False alarm is whether the spectrum hole has been correctly recognized or not. Based on that, you could have false alarms. Now, you want your false alarm to be very, very low, right? So the probability of false alarm expression is given here. And in that expression, you'll see that there are two parameters which need to be optimized. One is the gamma G, which is your threshold based on which you decide whether the cognitive radio user can transmit in that slot or not based on certain threshold. So you decide the spectrum hole based on that threshold. And the weight vector is denoted using the symbol W. So these are the two parameters which need to be tuned. And probability of false alarm. So you want your false alarm to be as low as possible, and you want your probability of detection to be as high as possible. So one is the first objective function needs to be minimized, and the second objective function needs to be maximized. And the parameters that we want to optimize while minimizing the first one and maximizing the second objective function are two in number. One is the weight vector W, and so here I have shown the W1, W2, Wm that forms the weight vector, and the decision device uses a threshold to decide whether the time frequency slot is a spectrum hole or not. That threshold is denoted as gamma G. So these are the two parameters which need to be optimized. Now, one of the ways to do this optimization is I can simply go for weighted sum objective function. So what I can do is, let's say I want my false alarm to be very low and my detection to be very high. So what I can do is I can assign some value to A1 and A2. Let's say A1 is 0.1 and your A2 is 0.9. So 90% I need, no, I am giving higher weightage to probability of detection, and I am giving lower weightage to probability of false alarm. So That means I am looking at an application where probability of detection has higher significance. Even if I lose something in terms of false alarm, that is manageable. That could be other way around, where the probability of false alarm needs to be focused, whereas probability detection can be traded off. So in that case, the values of an A1 and A2 can also be modified. So if I want to optimize this function, which is a combination of probability of false alarm and probability of detection, what I can do is I can simply go for single objective optimization and I can solve them. So here there are few single objective optimization algorithms. For example, genetic algorithm, particle swarm optimization, differential evolution, artificial bee colony optimization, right? Similarly, other two optimization algorithms. But these are all single objective optimization functions. And because we have combined these two objective functions into a single objective function, so that is why we are using single objective optimization function. And we can find out the parameters for which the probability of detection would be high or probability of false alarm would be low. Okay, so this is a difference. Uh, the graph shows the performance comparison between different single objective optimization algorithms. So as the number of iterations increase, we can see that the probability of detection subsequently saturates after a certain number of iterations. Okay, so now this is something which requires single objective optimization function. Okay, however, the problem is this weighted sum objective function is designed based on certain values of A1 and A2. So you predefine certain values of A1 and A2. For example, A1 is 0.1 and A2 is 0.9 or some combination, right? But for every combination of A1 and A2, this algorithm has to run, right? So for every combination of A1, A2, you will get a curve for each of these algorithms. So let's say you found out the best algorithm and you run it. But for every combination of A1, A2, I have to run and I have to store the final value for each combination of A1 and A2. Okay? So that becomes cumbersome as far as case by case algorithm run is concerned. Okay? So instead of that, is it possible to use multi-objective optimization algorithms? So when we look at the objective functions, most of the objective functions existing in a wireless environment are conflicting in nature, and we saw that in the previous case. For example, when you try to if you look at the probability of false alarm and probability of detection, you see that both are getting traded off. So you'll lose one in terms of the other. So that is the reason that most of the objective functions are conflicting in nature. So instead of running the single objective optimization algorithms case by case, means for every combination of A1 and A2, is it possible to get all the solutions for every combination of A1 and A2? Is it possible to get all the solutions in a single run? So that is where the multi-objective optimization algorithms show up. Okay. So in that case, what we can do is we can use any of the multi-objective optimization algorithms, whether multi-objective genetic algorithm, NSGA, multi-objective PSO, or any kind of multi-objective algorithms, but we'll get a set of solutions in a single run. So you don't have to go you don't have to solve the weighted sum objective function for each pair of A1 and A2. All the solutions would be available in a single run. So these are the parameter settings for four different multi-objective optimization algorithms. I'm not touching the uh, algorithms as such during this talk. I'm mainly focused on the application side. So let's say a multi-objective cat swarm optimization, multi-objective particle swarm optimization, multi-objective battle foraging optimization, and NSGA2. And FS stands for fitness sharing. So there is a variant of multi-objective PSO as well as others, where the fitness sharing can be brought in to improve the performance of the conventional multi-objective algorithms. Okay, so that is where the FS shows up. that is fitness sharing. So now you can look at the graph where your x-axis is probability of false alarm and y-axis is probability of detection. And this is a comparison between all the four algorithms. And you can see that all the solutions that are shown on the plot, you know, these solutions have been obtained using a single run. Okay. Now, every solution on this plot, okay, each point on this plot is nothing but the final value, final saturation value that you got in this plot. Okay, so that means if I run it for 500 times for each combination of A1 and A2, I will get 500 points in this plot, but that too in a single run. Okay. So that is the advantage of your multi-objective optimization algorithms, that you get multiple solutions in a single run. And you can see that when you are I said that the false alarm probability needs to be brought down and detection probability needs to be brought up. So you want your probability of detection to be as high as possible. Okay, but you can see the nature of the objective function. If your probability of detection is increasing, you can see that the probability of false alarm is also increasing, which we do not want. Similarly, if you decrease your probability of false alarm, that is what we want for sensitive applications. In that scenario, your probability of detection is also decreasing. So there is a trade-off. There is a conflict between both the objectives, and that is the reason that multi-objective optimization algorithms work very well when objective functions are conflicting in nature. Okay. So this is an example where two objective functions are shown which are conflicting in nature, and the when you connect the points for any specific algorithm, what you get is called as a non-dominated front. Okay, because each of these solutions can be considered as a candidate solution, because if you compare any solution, you cannot say that for any specific algorithm, not across the algorithms, but for example, if you look at the multi-objective lateral foraging optimization, if you compare any black dot with any other black dot, you will see that each of these black dots are actually a candidate solution. You cannot say that one is better than the other. Okay, because when you compare them, you will see that either one objective is improving and the other objective is degrading, or vice versa, right? So that is why they are called non-dominated solutions. Nobody can dominate on the other solution, but for each algorithm, not across the algorithm. Across the algorithms, we can compare which one is giving you a better solution. But for each algorithm, the solutions that we get are non-dominated in nature. So no one can dominate the other solution for each algorithm. This plot shows the runtime metrics. So how much set coverage metric is how much points could be covered in this particular front. So if you see the solutions that are offered by the multi-objective BFO, those are very less in number. So you can see the black dots are less in number compared to the multi-objective particle swarm optimization or other. So how many points are being generated by each algorithm, or how well you are able to cover the complete region of solutions, that is shown through set coverage metric. And as the generation goes on increasing, the set coverage metric flow is shown over here. Similarly, the moment of inertia metric that are used to quantify the performance of the multi-objective optimization algorithms. Okay. Now this plot shows that if the cooperativeness between the users increase by increasing the number of users. If I am increasing the number of cognitive radio users, you can see that the performance is improving because more number of people are now going to share information among themselves. So it is now easy to detect the spectrum hole than the previous scenario. So if you compare the first case, that is number of cognitive radio users is equal to 2, with the number of cognitive radio users equals to 20, so the black one and the red one, you can see that the with increase in the number of cognitive radio users, the information sharing increases, and hence the performance in terms of probability of false alarm as well as probability of detection improves. So that is how the multi-objective optimization shows up in the problem formulation of cooperative spectrum sensing. Similarly, when we look at the multi-objective optimization algorithms, they can also be used to design something called as cognitive radio engine. Now, cognitive radio is more like an adaptive radio, which can adapt itself looking at the environment, looking at the scenario. So, if we look at the cognitive radio engine, so you, at the center you have a cognitive engine, and you have a radio transmitter, you have a radio receiver. There are some channel statistics, right? And if you look at the block below, that shows radio parameters, which are knobs and meters. So on the right side, under the heading of knobs, you see transmit power, modulation, coding, symbol rate, antenna gain. All these variables can be tuned to get the best performance out of the cognitive radio. Now, how do you quantify the performance of the cognitive radio? On the left side in the circle, you can see the meters. Those are nothing but your performance metrics. For example, beat error rate, right? Signal power, battery life. So, you know, the performance of the cognitive radio can be determined in terms of beat error rate, whether the radio is using low power or not, whether the life of the battery is high or not. So on the right side, the parameters which are shown can be considered as variables which can be used to get the performance in terms of beat error rate and other performance metrics. So on the right side, what we have is the variables. On the left side, what we have is your objective functions. Okay. So for example, let's say we are now talking about two parameters. One is, let's say, transmission power, and the other one is, let's say, type of modulation. So say, for example, we are using different kinds of modulation techniques. Let's say if there is no modulation, then that is shown in terms of value 0 and binary phase shift keying, quadrature amplitude modulation. So all these modulation techniques have been encoded using some value from 0 to 7. And the transmission power is another variable which can have any value between 0 to 5 milliwatt. Okay. So now what we want is we want to find out what is the optimum modulation technique and what is the optimum transmission power, okay, to achieve three objective functions. Okay. What we want is we want the power consumption to be as low as possible, okay, and we want the beat error rate to be as low as possible, but we want the data throughput to be maximized. Okay, so there are three objective functions, and the formula for those objective functions have been shown in the slide. So where the variable n represents the number of users who are which are collaborating among themselves, and the other variables denote the corresponding parameters. For example, p denotes your power, m denotes the number of so the MRE, PSK, or say 8 QAM, then M is equal to 8, 16 QAM, then M is equal to 16. Okay. So now we want to minimize two objective functions, power consumption and beat error rate, and we want to maximize the third objective function, that is the data throughput. Okay. Now, similar to the previous case, what you can do is you can have a single objective optimization function where all three objective functions can be combined. But then again, you have to decide how much weightage you want to give to power consumption, how much weightage you want to give to beat error rate, and similarly how much weightage you want to give to data throughput. But then these weightage uh, so in the previous case, it was A1, A2. Now there are three objective functions. So A1, A2, A3, and all three values need to be decided a priori before optimizing the single objective function. So every combination of A1, A2, A3 will give you different solution. Okay, so to avoid that, we go for multi-objective optimization techniques. And you can see this is an example of a compromise solution obtained using multi-objective optimization algorithm as well as some fuzzy logic based strategy. Okay? Because your multi-objective optimization algorithms will give you a set of solutions. Now, out of those set of solutions, I am showing only a single solution here. Okay, and how we selected that single solution from the set of solution, we selected using fuzzy logic based strategy. Okay. So you can see the three axes. The three axes represent the three objective functions. One is the power consumption, the other one is throughput, and the z-axis is BER. So we can see that two objective functions need to be minimized, and the third one needs to be maximized. And the advantage of multi-objective optimal algorithms are already known to you. So we can run these multi-objective optimal algorithms and then get a set of solutions, and from these set of solutions you can choose any solution based on your application. So wherever the application is very power sensitive, so in that case you can give high, the solution can be taken uh, looking at the power objective function. Wherever you require your data rate to be very high or throughput to be very high, then you look at the throughput objective function and select the solution from the set of solutions that you have got from the multi-objective optimization function. Similarly, if you are if the application is more sensitive to bit error rate, you do not want high bit error rate, you want very, very low bit error rate. So in that case, you will select solutions which are close to low bit error rate objective function. So based on that, you can select a solution. So let's say if we select the red color solution, say for example the solution that we have got for multi-objective CAD swarm optimization with fitness AI. So now this is a solution, and this plot is showing you the solution in the objective function space. What this solution represents in the variable space. So if you look at the variable space, you can see, let's say you have, uh, let's say you have 16 subcarriers, okay? And the first one is the first plot shows the channel attenuation for each of these subcarriers, okay? So that is nothing to do with the optimization part, that is channel attenuation. Now the second and third plot shows our variables, that is transmit power and modulation scheme. So you can see that the transmit power is shown in the second plot, and the corresponding modulation scheme has been shown in the third plot. So wherever the modulation scheme shows 6, index 6, that means we are corresponding to 64 QAM. Wherever the modulation scheme shows 7, that corresponds to 128 QAM. So you can look at the modulation scheme and the transmit power and how the variation is happening to get this particular red color solution. So that is how the variable space looks like. So what that red color represents in the variable space, that is shown in your second plot and third plot. So this is how the 16 subcarriers can be allotted different modulation schemes and different transmit powers to get that particular red color solution in the objective space. Now, so say for example, this is one of the cases. If you select any other solution in this function space, so the corresponding plots for your transmit power and modulation scheme might be different. Okay. For example, if you select a solution which is very, very close to the x-axis, which is your FFC mean power, that is power consumption axis. So if you select any solution close to that axis, then probably you'll see that for lower value of power, you will see that the transmit power plot might be showing very, very low numbers, because that is your objective. You want your power to be minimized. The third application is in the field of wireless sensor network. Now, uh, when we look at the wireless sensor network, we have a set of sensor nodes which are deployed in a region of interest, right? Say, for example, you want to measure the temperature or humidity, you require a large number of sensors to be put up in that particular area, right? Now, if the sensors are cheap, then that is fine. I can, instead of 100 sensors, I can place 1,000 sensors. But if the sensors are costly, right, there are various temperature sensors which are very, very sensitive in terms of temperature accuracy, and those are very costly sensors, right? So if you want to use those costly sensors in any of your application, how do you place those sensors? Where exactly these sensors need to be placed? Okay. So this a third application links to the placement of those sensors in any particular area. Okay. Now this is a plot which shows 8 sensors which are denoted as node 1, no, sorry, uh, 9 sensors, node 1 to node 9, and there is one at the center which is called as high energy communication node, which has more battery power and other features, so that it can directly connect to the cloud server or the server, no, offline server that is near the farm. Okay. So if you look at this particular scenario, there are 9 sensors, and it's not necessary that all these sensors are directly connected to the high energy communication node. Okay. So, for example, your node 1 connects with high energy communication node through node 9. So, there is a hopping through node 9. Right. Similarly, node 3, node 4, node 5, node 6, they are not directly connected to the high energy communication node. Okay. Now, with a limited number of sensor nodes, how do you place these nodes so that various objectives are satisfied? What are those objectives? We'll look at that. Okay. So effectively, we want to deploy these sensor nodes at optimal locations. What are those optimal locations? Now, before we get into the multi-objective optimization algorithm, let's see how this sensor nodes are being modeled. Okay, so it is assumed that these sensor nodes are homogeneous except the high energy communication nodes. So all the 9 nodes that we are looking at, those are exactly similar in terms of the capability. But high energy communication node does have a higher a power source, higher computing capability, so that it can send the overall signal to the data processing unit or the server, which is either a cloud server or a offline server near the farm. Okay. The sensing coverage and the communication coverage of each node are assumed to have a circular shape without any irregularity. Okay. So let's say what is shown over here. Say for example, each node does have some radius over which it can sense the temperature or whatever variable it is observing, and it can communicate to the nearby sensor up to certain distance. Okay, so that is why the sensing distance and the communication distance, those are recognized using two variables, that is sensing radius and communication radius. Okay, so we are going to use those two variables down the line. So what are the design variables? As I have said, the design variables are where these sensor nodes are placed. So the 2D coordinates, x and y coordinates of all these sensor nodes, those are our variables. And since our focus is on finding out the solution using multi-objective optimization algorithm, uh, the simplest algorithm, that is Dijkstra algorithm, is used to find the shortest path from a node to the high energy communication node. There are other algorithms also to find the shortest path from a specific node to the high energy communication node. But since our focus is on the multi-objective optimization algorithms, I'm not focusing on the shortest path finding algorithms. So we are using the conventional Dijkstra algorithm to find out the shortest path. It is assumed that for every data transmission, the energy decreases by 1 unit. So what does that mean? That every node, when it communicates or sends a packet to the nearby node, it loses 1 unit of power. Okay, this is just for our convenience in terms of designing the objective function. That could be, say, let's say, for sending a packet, it might be losing some milliwatt of power. So that can be recognized as 1 unit. So with these assumptions for the sensor nodes, now we are looking at the objective functions. So what are the objective functions? The objective functions are two in this case. One is coverage and the other one is lifetime. Now, as I have mentioned before, the multi-objective optimization algorithms work very well when we look at the conflicting objective functions. Now, how these two objective functions are conflicting in nature, we'll see through various figures. So the first objective function is coverage. We want to cover the area as large as possible, but we have to also make sure that the network has a very good lifetime. That means none of the sensor nodes should die down because of high communication or why because of power, high power dissipation. So these are the two cases, and I am showing you how they are conflicting in nature. On the left side, you have a sensor network layout where all the sensor nodes are directly connected to the high energy communication node. Now, if they are directly connected to the high energy communication node, that means whatever data they are transmitting, that would be directly transmitted to the high energy communication node, and none of the sensor nodes are going to act as a hopping node. Okay, because all are directly connected to high energy communication node. So in that case, the nodes will only fail when the complete set of transmissions happen around individual nodes, right? So we can see on the left side, all the nodes are connected to high energy communication node, and the lifetime would be very high because they are only using their battery for their own transmission. On the right side, we have another example where the sensor nodes are far apart from each other, and you can see the coverage is very no much better than what you are seeing in the left side, because the sensors have a very low overlapping among themselves, so they are able to cover a larger region. But the problem is, now when they want to communicate to the high energy communication node, it has to be communicated through some other node. So for example, if one of the sensor node is at the corner of any at the corner of the rectangle, then what would happen is it has to send the data to the high energy communication node through some other nodes. Okay. Now, if if as a node, if it has to transmit its own data as well as some others data, then it would be using its power more often than what you see on the left side. So that means on the right side, the nodes will lose more power because whoever whichever node is being used as a hopping node, they will be losing more power for transmission of data for other nodes. Okay. So on the right side, what you see is a good coverage, but you know not a very good lifetime because because of because of the possibility that the hopping nodes would die down because of frequent usage. Okay. Whereas on the left side, you have a very good lifetime because every node is using its battery for its own transmission, but the coverage is bad. Okay, so we have a conflicting scenario. We have high lifetime, low coverage, and high coverage and low lifetime on the right side. So there are different kinds of models which are used in sensors for detection purpose. One is a very simple binary sensor model where up to a certain distance, let's say r sense is the threshold. So up to r sense, whatever detection has been done, that is correctly detected, and above r sense there is no detection. So the sensor accuracy is based on this r sense. So either it has detected or it is not detected. So it's a binary scenario. Okay. The second sensor modeling is stochastic sensor modeling, where up to certain distance, that is R sense minus RE, up to certain distance, the accuracy of detection is very good. That is one. Then subsequently, the accuracy reduces because the distance increases. So the sensing accuracy decreases up to certain point, and after certain point, that is r sense plus re, after certain point the accuracy completely drops to 0. Okay, so there is an exponential decay from 1 to 0, and this is a stochastic sensor model. Now we are using stochastic sensor model in this particular case. Okay. Now coming back to the two objective functions that we looked at, that is one is coverage and the other one is lifetime. So how do you actually quantify these objective functions? So the coverage is represented using this ratio. the denominator is nothing but the complete region of interest area. Okay, so this is normalized with respect to the complete area. On the numerator, what you have is the union of the area covered by each node, right? So, no, you can calculate the area covered, no, the circle area for each node, and then add them up, and then you get the numerator divided by the complete area that is considered as your region of interest. Okay, so that is your coverage. So how we did this? So for example, we divided this complete region of interest into grid points. Okay, so let's say for example we have 8 by 8 grid points over here. So 64 cells are there, and no, each grid point is labeled as 1 or 0 depending on the Euclidean distance between that grid point and the sensor node. So if a grid point is within the circle, sensing circle of one node, then that is assigned 1. If it is not within the circle, then that is assigned 0. Okay, and based on this, every grid point will have either a value of 1 or 0, and then in that case we can calculate the coverage approximately by summing all the ones that we have put up in this particular grid. Okay, so every grid point has either a value of 1 or 0 depending on whether it has covered by some certain sensor or not. Okay, so then the coverage can be calculated. The second objective function is your lifetime. So the lifetime can be calculated based on the time until which is one of the participating nodes run out of energy. Okay, so if any one sensor node runs out of energy, then the network is going to fail. Okay, that is the assumption. Of course, you can find out another shortest path, but then that is uh, that is a case where you have multiple, sufficient number of nodes available. Okay, so say for example, we have only one node which is linking multiple nodes to the high energy communication node, and that node fades, then that means the network is going to fail. Okay. So the lifetime is denoted as a ratio of T failure by T max. T failure is what is the maximum number of sensing cycles before any node fails. Okay, and uh, T max is what is the maximum number of possible sensing cycles. So the ratio of these two will give you the lifetime for the network. So how do link this T failure to the sensing cycle? So in every sensing cycle, the data is sent by each node to the high energy communication node through a route of minimum weight. And I have already said that we are using Dijkstra algorithm to find out the shortest path. Okay. Now, when you find the shortest path might go through multiple hopping nodes. Okay, so if the data of one node goes through two hopping nodes, then the intermediary two hopping nodes will spend some battery in receiving the data and transmitting it to the next node, or to the high energy communication node. So in that case, the energy for those two intermediary nodes would also decrease by 1 unit each. So that is how the T failure is being calculated. And T max is the what is the ratio of your total energy of any node and the energy lost for one data transmission, because every node is connected to high energy communication node. So this is the case. So this is the case on the left side, that every node is now connected to high energy communication node. So if I want to calculate the T max, what I can do is what is the energy for each node, maximum energy that is available with each node, divided by how much units are spent for transmission of one packet. Okay. So that gives you the maximum lifetime. So your T max is calculated as E total, that is the total energy of any node, divided by E loss, that is how much energy is lost for one packet data transmission. So so finally, when we look at the multi-objective optimization algorithms, what we have now is the variables are nothing but the two-dimensional coordinates of the sensor nodes, and the objective functions are nothing but coverage and lifetime. Okay. So which are conflicting in nature. That is what we have seen through those two plots, that the coverage and lifetime are conflicting in nature. So this is the flow chart for multi-objective PSO. I'm not going through this algorithm. I guess this must have been taught to you before. Okay. But whatever multi-objective optimization algorithms you choose, that can be used to solve this problem. So now, as I discussed, that we want our coverage to be high, which is the first case, and the first figure shows that the sensor nodes will go away from the high energy communication nodes, so that the coverage is very high. But the second case is the high lifetime case, where all the all the sensor nodes need to come close to the high energy communication nodes so that they can directly communicate. Okay? So both are conflicting in nature, and the variable is nothing but your two-dimensional x and y coordinates for the sensor nodes. Okay. So these are the parameters that I've chosen for multi-objective particle swarm optimization. And you can see with a single run and 10 sensors, uh, there are 7 solutions which are shown in this plot. Now, the x-axis is coverage and y-axis is lifetime. So you can see when your lifetime is very high, that is the first solution on top, that is, you can see that the lifetime is 1, but the coverage is very low. The coverage is of the order of 0.3, 0.35. Okay, because your all the sensor nodes are very close to the high energy communication node. But when it comes to coverage, okay, and the coverage has not touched 1 because this number of sensors are only 10 in number. Okay, so that is why even if the 10 sensors are away from each other and not overlapping, still the region of interest is large, and that is the reason that we are not able to have coverage of 1. Okay, but if you look at the last solution, that is giving you a coverage of 0.65 or so, but the lifetime is very low, around 0.2. Okay, so whenever you have a very good coverage, you have a low lifetime, and wherever you have a high lifetime, you have a low coverage. Okay, but all these 7 solutions are valid solutions, and you decide based on whatever application it is, how much coverage you want and how much lifetime you want. So based on how frequently you want to change your battery, you can decide how much lifetime you want with limited number of sensors, so that the coverage can also be taken care of. So you can see the coverage over here. This is one example. The coverage is 0.63709, but you can see the sensors are going away from the high energy communication node. So the lifetime of the network would be very low. Okay, because the sensors are trying to go away from each other, so that the coverage is high, but the lifetime would be very low. Okay. Now this is an initial disconnected network layout. Okay. Now these are the two extreme cases that I talked. Not the extreme cases, but two cases where your lifetime and coverage has been traded off. On the left side, you have a solution where the coverage and lifetime both are very close to 0.5. So this is more of a average solution or standard solution where I'm happy with good amount of coverage as well as happy with good amount of lifetime. I don't require very high coverage or very high lifetime. So left side is a solution where uh, all the sensors are not directly connected to the high energy communication node, but also they are not far away from each other. Okay, so the coverage is 0.5 and lifetime is 0.4. On the right side, you can see that the sensors have gone away from each other, so that is the reason that the coverage is higher, that is 0.63, but the lifetime is now low because there are, if you see, there are 3 nodes which are very close to high energy communication node, which are going to be used as hopping nodes for other sensor nodes. So if any of these 3 nodes which are close to high energy communication node die down, then your network fails. Okay, so that is the reason that the lifetime is very low, that is 0.199. So this is a plot where as we go on increasing the number of generations, we can we can have much better solutions. So that is how the multi-objective optimization algorithms work, right? If you go on increasing the number of generations, there is an improvement in your objective function. So the overall result is shown here. you know, now you can see the two extreme solutions are shown in the figure 2 and figure 3. Top figure is the initial disconnected network layout. So there is, the coverage is 0.63709, but the nodes are not connected to high energy communication node. Okay, so they cannot communicate with the high energy communication node. So even though coverage is high, the high energy communication node is not able to receive the signals from the sensor nodes in the initial network. On the left side, in the bottom, we have a coverage which is low, around 0.3, but you can see the lifetime to be very high, of the order of 0.999. So here is a solution where all the sensors are more or less directly connected to the high energy communication node. So lifetime is very high, but the coverage is very low. Right side, coverage is high because the sensors are far away from each other. The lifetime is low. Okay, because now the three sensors which are close to high energy communication node, they have to bear the expense of communicating the data for all other sensor nodes which are not directly connected to high energy communication node. So that is the reason that lifetime is low on the right side, because any of those three sensors fail, the network fails. So the overall conclusion is we touched upon three different problems. Okay. One is the cooperative spectrum sensing, where we talked about the conflicting of probabilities of false alarm and misdetection, or probabilities of detection. And the second problem that we talked about was cognitive radio engine, where we tried to optimize three objective functions: bit error rate, power dissipation, and throughput. And the third application that we touched upon is wireless sensor network, where the sensor nodes need to be distributed in an area, looking at the coverage and lifetime as two conflicting objectives. So while optimizing the network, we make sure that the connectivity of the network should be preserved. So it's not like the sensors can go away from each other by a big margin, but then the none of the nodes should no, there should not be a scenario where any node is not able to communicate with the high energy communication node either directly or through some hopping node. So the data of each node has to reach the high energy communication node. So that is why the fourth statement says that the connectivity of the network should be preserved. Every node should by some means get connected to high energy communication node. Okay. Some future directions, no, we can consider the energy consumption due to sensor movement. So wherever you have mobile sensors, in that case, the energy consumption due to the movement need to be taken care of. Other objectives which have not been taken into account in this study is your uniformity and the time and distance for sensor movement. So all those things can also be taken up as more objectives, and then the multi-objective optimization algorithms can be deployed to find uh, a set of solutions. These are few references related to the sensor network and cognitive radio, in case if you want to look at them in more detail. Yes, that's all from my side. If anyone has any queries, feel free to ask.
Dr. Pradhan,
Yeah,
you can unshare the screen. Yes. Now, hope you can able to see the participants chat box. So I
yeah.
suggest all participants to put their question in the chat box. Please write your queries in the chat box. Dr. Pradhan, today around 170 participants have attended your lecture.
Good to know that.
Participants, if you have any doubt, please type your queries in the chat box. Interference and latency. Somendra wants to know what is the role of interference and latency in the CGP.
CGP. So what is the CGP? That
Cooperative
Somendra is
game process.
okay. Okay. So okay. So that is not linked to this one. Okay.
Okay.
Fine. Although he has asked it. Okay. Fine. So if you look at the interference and latency in terms of the game processing, when we look at the cooperative spectrum sensing, that is also solved as a game theory problem. So that is not included here, but that is a separate topic altogether. So we can solve the cooperative spectrum sensing as a game theory problem also, where uh, when multiple users are sharing information with others, they should also get rewarded, right? Because they are going to share their information with you, so they are going to be rewarded also, right? So in that case, your reward and penalty things comes into picture, which is incorporated in the game theory. And there the interference as well as latency does have bigger roles to play. Now if I if there is a user who is facing more interference, and the information that is being shared by that user will be less rewarded as compared to any other who is having lower interference. Similar in terms of latency also. So that is related to the game theory concept, where we look at the signal to interference noise quality, so SINR, and based on that we reward or we penalize the users. So the rewardment factor is different based on what kind of signal to interference noise ratio uh, is obtained by each of these users. Similarly, latency also. Say, for example, if I am going to fuse the information from multiple users, what is the kind of maximum? What is the kind of latency that I can manage in this application? So, based on that, the latency as well as the interference factor comes into picture. But that has something to do with the game theory, which I guess is not part of my lecture class. But anyway, that's all what I have. So, can the carbon footprint or carbon emissions of a node or or a WSN layout be considered as one of the optimization objectives? Yeah, the carbon emissions, if it can be quantified, if you can quantify it and relate it to the battery power or the to so say for example, if your carbon footprint is different at different locations, then it makes sense to include that as a quantitative objective function. But if your carbon emission for the complete region of interest is more or less similar, then it won't have any advantage. But yes, of course, you can include them as a quantitative objective function, definitely. Hope it clears your doubt, Amritesh. What are the advantages of particle swarm optimization algorithm designed to solve optimization problems with multiple conflicting objectives when compared to other optimization algorithms in terms of convergence and efficiency? Okay. Now, see, I have shown the comparison between different algorithms. It's not necessary that your particle swarm optimization or a specific algorithm is going to work better in every application. That is not possible. Every algorithm needs to be fine tuned based on what is your application requirement, based on the sensitivity of the application. Uh, Imagine a scenario that, okay, there is an algorithm which gives you very good accuracy, but it takes 1,000 iterations to get that accuracy. But my application is such that I cannot handle that delay in my processing. So let's say my training part has to be finished in 100 samples. So if you talk about a wireless communication application, there is, you have to do the channel estimation within a coherence time interval. So for those applications where there is, time limitation, in those scenarios, even if the algorithm is performing very well in 1,000 samples, I cannot use it because of the time limitation. So it's not necessary that PSO is going to keep the test results. Uh, your attention on the parameters used in the mathematical modeling of the false alarm and detection. Okay. So when we look at the probability of false alarm, we looked at specific variables in this case. Okay. For example, if you look at the probability of false alarm, it is linked uh, uh, to the weight vector that is assigned to each of these. Yeah, yeah. I've gone back to the slides. You want me to share those slides once again?
The thing is, you can answer it because all those things are in recording in the YouTube.
Okay.
So the
So,
participant can refer it. You can just answer.
okay. So the probability of false alarm, included a Q function where your gamma g, which is your threshold, and the number of users n, and sigma, the noise standard deviation, and w is the weight vector, and the bigger sigma is linked to the sigma and delta that already specified in my slides. Okay. But among all these variables, the two variables which we have taken up as optimization parameters are nothing but your threshold gamma g and the weight vector for each of these users. So whether user one would be given a higher weightage or a lower weightage, that is one no, variable. The other one is what is the global threshold based on which I will decide that this is a spectrum pole or not. Okay. So that is how the false alarm and detection probabilities are designed. But these expressions are very conventional expressions. If you want to look at the expressions for probability of false alarm and detection for a specific scheme, for example, let's say you want to look at false alarm and detection for spatial modulation or for any other modulation scheme, then the expressions would change. Is that okay, Suman? Can you suggest the base article for incorporating the wireless sensor network with nature-inspired algorithms? There are plenty of IEEE papers which link wireless sensor network with
Dr.
the
Pradhan,
evolutionary
your
algorithms.
article is also very popular. Of the last years that I have observed, it has got a lot of citations. Yes.
Yeah,
So
I
participant,
won't say
you
that
can refer his manuscript also. Yes.
yeah, Rajsekhar, if you want to refer to my article, feel free to refer to that article. But there are plenty of articles which are linking wireless sensor network with evolutionary algorithms. So probably if you search in IEEE, you'll get many articles. Hopefully, I didn't miss any queries in between,
No,
right?
no, no, no. Fine. I am looking at that.
Yep.
So as there are no further queries from the participant, so let's thank Dr. Pradhan for such a wonderful presentation for last 1 hour. It was really motivating for all participants to know the application of optimization algorithm in such real life scenarios. And tomorrow also we have a very interesting session from Professor Pradhan. So we are also looking forward for the next session tomorrow.
Yeah. Thank you very much, Dr. Nanda. Thank you very much, Dr. Sharma and other organizers. Thank you to all the participants. Hope no, this is not everything as you imagine while you study multi-objective optimization. These are only three specific applications related to cellular communication and wireless sensor network. When you go through IEEE, you will probably find thousands of articles linking various objective functions related, to multi-objective optimization algorithms. So feel free to go through those articles. If you have any queries, my email ID is also listed in the title slide. It's also available. So in the brochure. So feel free to write to me if you have any doubts related to these contents. We'll meet tomorrow once again with some new topic. So thank you very much, everyone.